Okay, continuing on with our playlist on Laplace transforms, we're asked to find the Laplace transform of a times t, where in this case a is going to be some constant value. Over here to the right, we've got our definition of the Laplace transform, and I'm just going to use this in order to try to find our solution for the Laplace of at. Now, one thing I mentioned in a previous video, you could actually just pull the a out in front. Because the Laplace transform is an integral and you have a constant, the same way you can pull a constant out of an integral, you can pull a constant out of the Laplace transform. But I'm just going to do it out and we'll write this. This will be our f of t in this. We'll use this as our f of t. So let's see, we're saying that the Laplace of at is going to be the same thing. This, using the definition, we're going from 0 to infinity, e to the minus st, a times t dt. And we'll just go ahead and integrate this. I'm going to use integration by parts on this. We'll do the DI method or tabular integration. And what I'll do is I'll differentiate a times t and integrate e to the minus st. Derivative of at is just going to be a, and then taking the derivative again, but the derivative of a constant value is just going to be 0. Then here, taking the integral of e to the minus st is going to give me e to the minus st over minus s. And then doing it one more time, we pull out a minus s again, this becomes positive s squared. So then we have a 0 in the last row, so we don't have to integrate this last row because it's just 0, but we'll have our solution here on the diagonals. Now when I write this down, I can factor an a out in front because we've got an a in both these terms, and we also have an e to the minus st. So I'll factor that out. So then this first term is going to be minus t over s, and then the second term is going to be a minus 1 over s squared. And actually what I could have done is factor a minus out, so let's just do that now. We'll change these signs to pluses and we'll factor a minus out front. And then we just need to evaluate this thing from 0 to infinity. Now when we evaluate this at infinity, we need to be careful of a few things. If s is negative, then this is a positive coefficient. We plug in infinity, e to the infinity, and then the whole thing diverges. So we can't have that. So I'm going to we'll just set the condition that s needs to be greater than 0 in order for this to converge. But then even with this condition, technically we get an indeterminate form. As you plug infinity in here, this piece is going to 0, but then you have infinity here. But if you do the limit out, this term is going to be way more powerful because it's an exponential. So evaluating this at infinity, this whole thing is going to 0. And then evaluating this at 0, let's be careful again. We're going to have minus a. We plug a 0 in here, e to the 0, that's going to be just a 1. Then within the parentheses, we plug a 0 over s, that's just a 0. And then we have plus 1 over s squared. Let's just clean this up. This 0 is nothing. Distributing minus times minus is going to be a plus. So if we just distribute in our a here, we end up with a over s squared. And so we'll just write this in up here too, a over s squared. You'll just notice when a is 1, we get 1 over s squared. So our Laplace, if you just want the Laplace of just t, that's going to be 1 over s squared. So there you have it, Laplace of at. We'll keep going with more of these examples. So we'll stop it there. Thanks everyone for watching. Have a good day.